Today I will cover momentum, impulse, and impulsive force. Okay, so let's start with momentum. Now, momentum, so all of you know the formula. How do we define it? In simple words, momentum is mass into velocity, okay, denoted as P. So mass in kg, velocity in ms minus 1. So formula kg ms minus 1. And because momentum has a velocity, so it makes it a vector. If I say an object moving in this direction, v, then it has momentum in that direction. If I want to change the momentum, the force that I apply must be in the same line as the momentum vector. So to change the momentum, I can apply force in the same line. So it's parallel to the vector. If you apply force in this direction, then you cannot change the momentum of the object. Okay, now in the study of momentum, right, it is a very, very important chapter. Why? Because momentum, it talks about mass in motion. Anything that has mass and it's moving, then it has to do with momentum. Now, if you look at everything around you, everything around you is constantly moving. Nothing ever stays stationary in this universe. If you argue, you say that, okay, I'm sitting here, I'm not moving. But because you are attached to the ground and the earth is rotating, so you are also rotating with the earth. How fast you are moving with the earth? You're rotating at 1,000 miles per hour. That is the rotation of the earth. So technically speaking, you're actually moving at 1,000 miles per hour. Everything attached to the earth is moving. If the earth suddenly stopped moving for 1 second, what happened? If the earth stopped moving for just 1 second, then you will smash into the wall in front of you with a speed of 1,000 miles per hour. Okay, so everything you see, the atmosphere, the atom, if you look at the molecular structure inside all the molecules, atom, they are also vibrating. They never stop and stay still like this. It doesn't happen. It doesn't exist. Okay, so everything is moving. So everything has momentum. So momentum becomes a very important chapter. Now, momentum, in this chapter, you need to know the conservation of momentum. Conservation of momentum says what? Okay, it says that the momentum in an isolated system is always the same. Okay, what does that mean? Okay, now let me break it down like this. First, you have to understand a system. What is a system? If I say the Earth system on the Earth, there are the atmosphere of the Earth, people on the Earth, objects on the Earth, material on the Earth. All this, they mix up the Earth system. So these are the member, mind the words, the member of the system. If we look at another system, Mars, that is the Mars system. The atmosphere of the Mars, objects on the Mars, river, water on the Mars, all that, they mix up the Mars system. So they are the member of another system. So you have different system, okay? And each system, they are different from one another. That is a system. It is something that we study. If we study a system, for example, we study the Earth system, we don't care about what is outside. We don't care about the Mars system. We don't care about the Jupiter system. Those are irrelevant. Anything outside the system, we don't look at it. We only focus on our own system. Okay, now, so in any one system, there can be a lot of members, right? So all these members, each of them, they are moving in their own velocity. Here, we have a system of 5 members. They each move at their own speed. So each of the member, they have their own momentum. Okay, so when you add up the momentum of each and every object here, this one you add with this, this, you get the total momentum of the system. Here is my system of 5 bodies. I add up all the momentum, I get the total momentum of the system here. Okay, now when these 5 bodies, they come together, let's say they come together and then they collide. They collide with each other and then now they move away from one another. So there's a collision happening here. Okay, the collision, we said that it is an incident. An incident can be anything, collision, explosion, anything. So these 5 bodies, they come together, they collide, and then now they move in different direction and away from one another. What happened to their speed? Their speed after they collide surely have changed. So their final speed is not same as their initial speed. If you look at just one individual object and you observe the momentum before when they collide, and after they collide, just focus on one individual object, one member, their momentum have changed. This one, the momentum also have changed because the velocity changed. This one have changed, this one have changed. Every one of them, momentum have changed. But if you add up everything after they collide, this one plus this one plus this one plus this one, the total momentum is the same as the total momentum before they collide. So meaning that here, there's a total of 100 momentum, 100 kg ms minus 1. When they come together, they collide, bounce away. Still, if you calculate the total momentum, it will be 100 kg ms minus 1. It cannot be 99, it cannot be 101. It must be exactly 100. That is the principal conservation of momentum. Okay, so in any system, total momentum is the same. Is there any condition? Is it always the same? There is one condition. This condition is that there cannot be an external force acting on it. External force like frictions. Okay, now let's say, let me draw this here. We have a system of 5 bodies. 1, 2, 3, 4, 5. Moving towards each other. So anything outside, I don't care it. So this is my system. This one is having velocity u, mu, 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 mu. Total up everything, the momentum, you get sigma P1. That's the total momentum. Now, what is the incident here? The incident here is collision. After they collide, now they move away from each other in random direction. Their velocity has changed. So we have mv, 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 mv. Total up everything, still the same system. Okay. Sum of momentum number 2. These 2 momentum, they must equal. This one equal to this one, regardless. For example, the 5 body here, after they collide, 2 can go here, 3 can go here. They can go in separate ways, but the total momentum must be the same. Okay. Now, condition is no external force, right? So what is an external force? What is a force? Force, you have learned about it. How do you define it? Force can change the momentum of an object. Let's say I have one object moving in this direction, moving at speed v. So it has momentum in this direction. Okay. Now, if I try to stop it, before I stop it, this object by itself, it is a system. Okay, it is moving in its own system. Suddenly, from outside, suddenly I come in. I come into the system and then I try to stop the object. I apply a force and I bring the object to stop. Okay, I have changed what? I have changed the velocity of the object, and thus I have changed the momentum of the object. The force that I apply, I can change the momentum of any object. So force is defined as something that it is an agent. Force is an agent that can change the momentum of an object. So when I step in the system, this is my system. Let's say I step in and then I apply a force on one of the body. What happened? This force, initially, it doesn't belong to the member in the system because I'm from outside. I'm not a member of the system. So when I apply the force, this is an external force. So this force will disturb the momentum of the body in the system. So when I go and push one body, then I have added extra momentum to the bodies inside the system. Similarly, if it's friction, then the friction will take away the momentum in one of the bodies in the system. So if there is external force, then your momentum after the collision, the P2 here, will be larger than P1. They no longer equal. So if they no longer equal, we cannot say that momentum is conserved. Momentum is not conserved. That's why if you have external force, momentum is not conserved. They do not equal. The word conserve means before equals after. Okay, before equals after. Now, you see, when the balls collide with one another, they also exert a force, right? This body hit another body, also apply a force. So let's say the force applied by this body here. Is this force external force? No. Why? Because this force, who is applying the force? The body, the ball is applying the force. And the ball is a member of the system. So that force comes from a member of the system. So that force is not considered external force. That is an internal force. So you have to be very clear, what is internal force? What is external force? Internal force is the force applied by a member of the system. External force is the force applied by something that is not a member of the system. So there is internal force everywhere, still momentum is conserved. Because the condition is only cannot be external forces. Okay, so this one is the conservation of momentum. Okay, now let's look at one example here. Okay, you see the equation, the formula is still the same formula. Okay, it's still the same one. So it's like, let's say, suppose that we got two bodies, M1 moving at U1 in this direction, M2 moving at U2 in this direction. Two bodies and they make up a system. This is my system. Before the collision, now let's say the body at the back catches up and it hits the body in front. So there's a collision here. Now, that collision creates a force. A force is produced. Who is producing the force? This go and hit this one. So the force is applied by this body here. And this body is a member of the system. So this force is internal force. So our momentum is still conserved here. After the incident, when the ball go and hit the front one, the ball in front gains speed and the ball at the back loses speed. It's like a truck hit a car in front. Okay, the car gains speed and then the truck slows down. Okay, so here this body loses speed, so you have new speed, final speed, and then still in the same direction, and the body in front, M2 V2 here. We are going to ignore friction. Gravity is okay. Is gravity an external force? Actually, gravity is an external force, but gravity is an exception here because gravity, it acts on every single object. Okay, every single object. So we can cancel out the effect of gravity. So whether is it external force, internal force, doesn't matter. We can cancel out. It acts on every single object. So the external force we are talking here is mainly air resistance and friction. So we are going to assume that there's no external force and momentum then will be conserved. So we can write an equation m1 u1 plus m2 u2. That's momentum total before, right? Equals to total after m1 v1 plus m2 v2. And this equation applies everywhere, regardless of the location, regardless of the object, as long as there is no external force. You can apply this in planetary collision. One planet collide with another one. Galaxies, same. We can apply the same theory. As long as the condition is fulfilled, there is no external force. So this is our momentum equation. And when we talk about collision, there are many types of collisions, right? There are two types, elastic and inelastic. Inelastic, still they follow this. We use this equation. Just that for inelastic, for objects that stick together after they collide, they share the same speed, right? They share the same speed, then these two speeds would be equal. This speed and this speed would be equal. If this two speed is equal, then we can factorize out m1 plus m2. You get another one. Actually, it's the same thing, just the derivation. So this is applied for inelastic collision. What is elastic and what is inelastic? The main thing that differentiate these two. Now, in SPM, the way we differentiate them, we said that objects stick and objects do not stick, right? After collision, if they do not stick, like if you kick a ball, bounce off, do not stick, that is elastic. And inelastic is something that after collide, they stick together, like one planet collide with another planet and they stick together, they become one single body. That is inelastic. Or it can be one plasticine hit another plasticine, become one single body. That is inelastic. Okay, now in A-level physics, if you want to differentiate between elastic and inelastic collision, you have to talk about the kinetic energy. Okay, you have to talk about the kinetic energy. So you need to prove that kinetic energy before, if it's equal to after, then that is elastic. Before and after. Okay, so you need another equation. 1/2 m1 u1 plus 1/2 m2 u2. That is the total kinetic energy before, equals to 1/2 m1 v1 plus 1/2 m2 v2. So this is the conservation of energy. Total kinetic energy before equals after, that is elastic. Total kinetic energy before do not equal after, that is inelastic. So the question, if they ask you, is this elastic or inelastic, you have to show the calculation of kinetic energy. Before, is it equal to after? So two formulas here we are going to need. Okay, 1 and 2. Okay, now let's look at one typical example that you probably are familiar with. This one. Recoil of gun. Okay, now here we have a system of two bodies. The gun and the bullet. 2 kg and 20 gram. Initially, they are not moving. So the system is at rest. Suddenly, I hold the gun like this, and then I push the trigger. So I open fire, and then the bullet travel at a speed of 500 meter per second. And at the same time, the gun recoil back. Okay, what is the incident here? The incident here is the firing. Okay, firing. The previous example is the collision. So the firing separates before and after. This is before, this is after. Now, a force is produced when I push the trigger. Where does the force come from? The force comes from the bullet, the powder, the gunpowder. Okay, and it comes from the gunpowder, which is in the bullet, and the bullet is a member of the system. So the force produced is external or internal. It is an internal force. Okay, so the force that is produced to propel the bullet forward is an internal force. So if it's internal, then momentum is conserved. And at the same time, I'm holding the gun like this, still. I'm not moving the gun like this. Okay, I'm not moving it to the front, I'm not moving backwards. So meaning that I'm not applying external force. I'm just holding it still like this, okay, like this. And then I press the trigger and it recoils. So all the forces comes from within the bullet. I did not apply any force on the two bodies. So this is very important. So there's no external force. Momentum is conserved. So if momentum is conserved, then we can write m1 u1 plus m2 u2 plus m2 v2. Okay, let's take m1 as the gun. So m1 2 before is all 0, right? Because all at rest. So this would be 0. This would be 0. m1, that's 2 kg. v1 is the one that we want to find. m2, it's 20, okay, 0.002. What is this? 0.02 kg. And v2 is 500. When you use the formula, be careful with the sign, guys. If the velocity is pointing to the left, then you have to add a negative. Okay, because this v1 is the unknown that I want to find, so I don't add the negative. But if the number is given, for example, like 5 ms, then you have to add a negative in the calculation. So 0 equals to 2v1 plus 0.02 times 50. Okay, plus 1. Okay, 0.02 times 500, 10. Okay, and then v1 equals to negative 10 divided by 2. That's negative 5 ms minus 1. So v1 negative 5, meaning that the recoil velocity is moving to the left at 5 meters per second. This velocity is considered very large. If the gun hit you at 5 meters per second, that is very painful. Okay, it might cause fracture. Now, what happened in the military training? They are trained to hold the gun very tight and very firmly. What happened is that they will press the gun, the back of the gun, they press the back of the gun against their chest. Okay, they hold the gun close to them and then they press it against their chest. Why they want to do this? You see, if they hold the gun in front of them, okay, then the mass is only from the mass of the gun, 2 kg. If I hold it against my chest, then my body, my hand, and the gun all together, they become one single body. Meaning that I have increased the mass. Okay, I attach my own body mass with the gun so that they become one single body and the mass increases. So by doing that, what happened is that the M1, now I have increased it to, let's say if your body mass is 80 kg, plus, now this is your body mass plus the mass of the gun, 2 kg. So you have 82 kg, right? So 0, recalculate it. 0 equals to 82 V1 minus plus 10. So we have V1 equals to minus 10 divided by 82. That becomes negative 0.12 meter per second. From negative 5 meter per second, I have decreased it down to negative 0.12, which is now a very small velocity. Just by doing one simple action. Press the gun against your chest and you hold it as tight as you can. You can minimize the recoil velocity based on what? The principal conservation of momentum. Okay, so that is one application of the conservation of momentum in real life. Okay, now we are done with momentum. Now, momentum, and then next one we talk about impulse and impulsive force. Okay, so how is momentum related to impulse and impulsive force? You see, impulse is the change in momentum. Okay, impulse is the change in momentum. Okay, let me go back to the slide first. Very quick. Okay. Okay, now you see, let's say we have learned about the force formula F equals to ma. This one means that when I apply a force on a mass, m1, for a duration of t, then this mass will accelerate at an acceleration of a. This is a uniform acceleration. Okay? Because the F equals to ma, the F is uniform, net force, and the A is also uniform, constant acceleration. So if I apply a constant force, then it will accelerate for t duration of time. That is this formula here. So if we sketch the graph, F against t, F t graph, how does it look? Okay, you should get a horizontal line because the force is constant. And the time period, this is t, same as this t here. This is the FT graph. And if I calculate the area under the graph, what is the length? The length is t, and the width is the y-axis f. So if I calculate the area equals to length times width, that's f times t. What is this ft? Ft is change in momentum. Okay, f times into t, that's impulse, right? So change in momentum equals to impulse I. F is unit, is Newton, t is second, so impulse having a unit of Newton second. So impulse is a change in momentum. If the mass started at rest, then the force that I apply changes the momentum, right? So how much momentum it gained? How much momentum it gained? That gain in momentum is going to be equal to the change in momentum here, if the mass started at rest. Okay, so if I give it this amount of momentum, then it gained this amount of momentum. So the change of momentum is equals to the momentum gain. P gain is equals to change in momentum if mass at rest initially. Now, but in reality, right, not all forces are constant. There are some forces, they varies. They are a variable. They are not constant. For example, like forces that acts in a very short period of time. Okay, that forces resulted in impact. Okay, impact force. Impact force, they act in a very short period of time. Now, how does impact force works? Let's say this is a ball, and the ball is a little bit, is not very hard, it's a little bit flexible, right? So meaning that it can deform, you can press it. So this is the surface of the ball. Let's say I kick the ball. I kick the ball and we put it into slow motion. Imagine that we put it into slow motion, we take like millisecond timestamps. Okay, it's like millisecond frame. So what happened? So when you hit the surface of the ball, what happened to the surface? The surface first, it will deform. It will be pressed inward like this. Before the ball move, the surface will deform first. Okay, so meaning that the force applied, if I were to sketch the graph of the force against time, how would it look like? This is F, this is T. The graph will look like this. Initially, it will be very small, and then slowly it increases. Okay, this is when it deforms more and more, then the force it's getting nearer and nearer to the center of the ball. And at some point, it will start to move the ball. Okay, imagine slow motion. At some point, it will start to move the ball. So initially, it deformed first. So the force rises. It started very small, and then it rises. Eventually, it will reach the peak, and then it will come back down, drop. This peak is when the ball starts to move. So this is the force over time. And the time period here is very small, it's very short. It's like a fraction of a second. So in short period of time, force can be variable. This force is changing over time. What do we call this force? How can we calculate this force? Can we calculate using F equals to ma? Cannot. Why? Because this F equals to ma, you can only put one value. Which value you're going to put? You got so many value of F here, you cannot put. So this one, we cannot use this. Okay, because at any time, the force is different. T1, T2, T3, they have different value of force. So we cannot calculate using F equals to ma. So how do we calculate it? By the way, what is this force called? This force is we call the impulsive force. So you know, impulsive force is what? Is a variable force. It's a variable, meaning that it is changing and is due to impact. Now, same as this FT graph, if I take the area under the graph, it is the same as impulse. So area under the graph is also change in momentum, and that is also impulse. But this area is a little bit difficult to calculate. This is square, you can just length multiply with. This one, what do you have to do? You have to integrate. Integration, remember integration, you can calculate the area. But we are not going to do integration here. And you are not required to do integration. Okay, we can just use estimation. Okay, what we do is we take the peak, we draw This is the time T. Okay, let's call this TO. And this is T4. This is the duration where the force acts. From the moment it starts to deform to the moment that the force like taper off. Okay. So here, the duration where the force acts, here, okay, we can draw a triangle like this, and then like this. Oh, sorry. This. Okay. So we are going to estimate, we can calculate the area of the triangle, and we estimate that the area of the triangle is same as the area of the bell curve. Okay, this bell curve shape here. So if you calculate the area of the triangle, then that is equals to the change in momentum. So if the ball is at rest, then this change in momentum will be the momentum gained by the ball when you kick the ball. Okay. Now, the average force, not average force, the impulsive force, it is changing, right, over time. So how do we calculate it? If I want to calculate the force, the impulsive force itself, the way you calculate it is we take the average value, because it is changing. So we cannot get one value. We have to get the average. So the force looks like, the graph looks like this. Okay, now this is the graph. We find the average and somewhere here, closer to the bottom, somewhere here. This is the time period T0 and T4. This somewhere here, we draw a line and we call this the F average. Okay, now this line has to be very accurate, that if you draw a square between T0 and T4, this area of the square must be the same as the area of the bell curve. So if I call this A1, the area of the square A2, and A1 must be the same as A2. So we are not changing the graph, because the area, what's the area? The area is the change in momentum, right? So the change in momentum must be the same. That's why the area has to be the same. Imagine like you change the bell curve graph. You make it like you take it down and then you change it to a square graph. Okay, a square graph. So that line, this line is your average force. And this, we call it the impulsive force. So impulsive force is actually the average calculation of a variable force. From here, we know that area equals to change in momentum, right? mv minus mu. And then area also equals to this square, the length times the width. What is the length? The length is the time duration where the force is applied. Let's call it T. And the width is the average force. So I can write it as F average times into the duration. This is actually the area of the square here. Okay, so F average times T, and these two are equal, so I can write F average T equals to mv minus mu. Bring the T over there, I get F average equals, and you get this formula that you are already familiar, mv minus mu over T. What is the T? Again, this T, what is it? It is the time duration where the force acts. The ball, remember the ball, when I touch the surface, it starts to deform. It starts there, T0, deform and then travels, and until my foot leaves the ball, the T ends there. That is the time. So it is the time of impact. Okay, and we can also see the longer the time, the shorter, the longer the time, the smaller the average force. The shorter the time, the higher the average force. So in any impact, if we can lengthen the time, we can decrease the force. Like in long jump. Long jump, when you land on the ground, let's say without a mattress, you land on the ground directly. Because the ground is hard, meaning that the ground does not bend. It does not allow bending. The molecules inside is fixed, is hard. Okay, it cannot deform. So the moment you land on the ground, what happened? You are moving at, let's say, 10 meters per second speed, falling down. The speed is the speed before you touches the ground, not the speed up above. No. Okay, your speed up there, let's say is, okay, 1 meter per second. Okay, down here, your speed has increased. So the speed is, we take the speed before you hit the ground, not up there. Okay, now when you hit the ground, suddenly your speed before you hit the ground is very large, because there's an acceleration every second. You're accelerating at 9.81. By the time you reach close to the ground, your speed is very large. When you hit, the speed suddenly goes to zero. Why suddenly goes to zero? Because the ground do not bend, it is not flexible. So meaning that your momentum drops to zero in a very short period of time. So yeah, there's a change in momentum in a very short period of time that result in a very high force acting on your feet. Okay. Now, if you put a mattress, because the mattress, if you go in the structure of the mattress, the molecule, they can be compressed. Okay, they can be compressed. So the moment you land on the mattress, what happened? Your speed does not decrease to zero immediately. It compresses the mattress down a certain distance. Then only your speed is zero. This is the mattress. When you land here, when your speed hits zero, your speed hits zero maybe somewhere down here. This is where your speed is zero. If it's on the ground, the moment you land on the ground, your speed hits zero immediately, because this surface do not bend. Okay, so this lengthen the time of impact, and your impulsive force very, very small. Same as you jump into the sea. Okay, into the sea. So when you land, where is your speed? Okay, your speed here v1, and then you go down somewhere down here at a certain depth, only your speed is zero. So there is a buffer. Okay, there is a buffer. So the impulsive force become very, very small. Okay, so understand that impulse, the point of this, what is the bottom line? Understand that impulsive force is a variable forces. And how do I calculate that? I get the average. Okay, in the exam, you will be given graph like this. Okay, this bell curve. Whenever you see this bell curve, okay, it's impulsive force, a variable force. Okay, now we look at a few examples of calculation. Okay, let's say I erase this. Okay, suppose that I drop a ball 2 kg and it falls down 10 meters and it hits a metal plate. After it hits the plate, it bounces up at a speed of 10. Okay, let's just put this aside first. At a speed v. Okay. Find the change in momentum of the object. Find the change in momentum. Okay, how do we do this? Now, to find the change in momentum, we know that the formula is change in P, mv minus mu, right? Okay, mv minus mu. So the m is the same. I can just take out the mv minus u. The v is the v after the bounce. The u is the u just before it hits, just before it bounces. So it is not the u up here. Okay, be careful not to choose the wrong u. So the u up here, this is at 10 meters from the plate. So you have to calculate the velocity just before it hits the metal plate. So that meaning that you have to do the Suvat calculation. Okay, so u is 10 meters per second, and then you have your g is 9.81 meter per second square. S is 10 meters. You find the final velocity just before it hits the metal plate. So v square equals to u square plus 2as. Okay, 10 square plus 2, 9.81. All are positive because what is the initial direction? Down. So I take down as positive. Acceleration is also acting down, so it is also positive. So no need to worry about the sign. 2, 9.81, and then 10. Calculate this, we get okay, 17.21. Okay, because all are in 3 significant figures, 3 significance, 3 significant. So I approach it as 17.2, also 3 significant figure. So this 17.2 is the velocity before it hits the metal plate. Now, let's assume that the velocity after bounce is 10, also same 10 ms minus 1. Calculate the change in the momentum. Okay, so equals to m, that's 2 kg, minus 10. Okay, you have to put a minus for the final velocity because now after the bounce, the velocity is moving up. So we take a minus 10 and then minus the initial speed, downward 17.2. Okay, so minus 10 minus 17.2 times 2, we get minus 54.4 kg ms minus 1. This is the change in momentum, and okay, or I can write ns. Minus 54.4, there's a minus because momentum has a vector. So change in momentum also has a vector. So it has a sign, minus 54.4. Okay, now let's say B, we want to find, calculate the average force in addition to the weight of the ball. The plate exerts on the ball if the contact is 0.14. Calculate the average force in addition to the weight the plate exerts on the ball if the contact time is 0.14. Okay, so meaning that we want to calculate the impulsive force. Okay, so impulsive force, F average, equals to impulse divided by the time. So negative 54.4 divided by 0.14. So we get negative 388.57. Three significant figure, so negative 389 Newton. This is the force. Why it has a negative? Okay, negative means upward, right? We are taking downward as positive. Always take the initial direction as positive. Okay, so negative 389, meaning that this force is opposing the motion. How come? You see, there are two bodies here. The ball and the plate. If you remember in our last lesson, I talked about Newton's third law. Okay, when the ball hit the plate, what happened? The ball hit the plate, there's a force produced on the plate. F ball on plate. And due to this action, there's a reaction produced. So that reaction is acting on the ball. That's F plate on ball. Since we are taking downward as positive, meaning that this force is a negative, this force is a positive. So you are calculating this one here. You are not calculating this one. Although they are the same in terms of the magnitude, but sometimes you have to be very clear which force that you are calculating. It is the upward force that you are calculating, and this force is the force acting on the ball, not on the wall. There's a difference. Okay, so this force negative 389 is acting on the ball. Okay, so if the question says what is the force acting on the wall, then I change F AVG is equals to negative, no negative, that's 389 Newton, same as this one, but without the negative, because the force on the wall or on the plate is downward, is a positive. Okay, so this is on ball, that's why it has a negative and it's upward. This is on plate, like this. If the question asks you justify, okay, why justify your answer? Because action and reaction. Which one is the action? This is the action. Which one is the reaction? This is the reaction. So these two, they are equal but opposite. Equal in magnitude but opposite in direction. Okay, so in any calculation of the impulsive force, there will be a negative, and meaning that the force is always, you are always calculating the force acting on that object, that incoming object. Okay, if you want to calculate the force acting on whatever the object being hit, that is a positive force. Okay, action and reaction time. Okay, now A, B. Okay, let's do C. Okay, we haven't finished. This is the force acting on the ball, right? This is due to the impact force. And the question says, in addition to the weight, you have to include the weight. So what happened? The weight, what is the weight? Okay, 2 kg, right? So 2 times 9.81. That's 19.62 Newton. Okay, so 19.62 Newton is acting when the ball hit the plate. There's an extra 19.62 Newton. That is the weight of the ball. And at the same time, there's also an extra reaction upward, 19.62 Newton. So this one is negative 19.62. This is on the ball. It is acting upward. So the total force acting on the ball, you add negative 389 plus 19.62. Okay, right here, F total equals negative 389 plus negative 19.62 becomes negative 409 Newton. You can write 409 and then upward. Okay, that is your answer. Deduce whether it is elastic or inelastic, C. Okay, now this one I mentioned earlier, you have to talk about what? The kinetic energy. So you can calculate the kinetic energy before half mu square. Now be careful, the U is not the U up here, no. It's the U before it hits. That is the one that you calculated, 17.21. So it's half times 2 times 17.2 square. 0.84 joule. And final, kinetic energy final, half times 2 times 10 square. That's 100 joule. Is it the same? No, not the same. So energy is lost, Ke lost. What is the Ke lost? Minus 195.84. So if there is kinetic energy is not conserved, then this is inelastic collision. Inelastic collision. Okay, then the question asks again, D, what is the max height the ball can reach? What is the max height the ball can reach? We can calculate this using the energy. Because you know, after it bounces, what is the kinetic energy leaving the plate? This one, 100. Right? Kinetic energy after the bounce is 100 joule. So meaning that this kinetic energy is going to be converted to potential as it rises. Okay, so potential at the top, at the maximum height, is where the potential energy is the same as the kinetic energy. So we take Ke loss is the same as the potential energy gain. Okay, Ke loss as it rises, the potential energy gain. So 100 joule equals to mgh. Okay, actually we can take out the, okay, m you put in 2 kg, 9.81, and h is 5.10 meter. This is the maximum height after bouncing it can reach. E, one more. State and explain whether linear momentum is conserved during the bounce. State and explain whether linear momentum is conserved during the bounce. Is there external force? We assume that there's no friction. So, yes, if there's no external force, momentum is always conserved. So yes. And then we talk about what? Momentum. What happened to the momentum if it's conserved? When the ball hits, okay, it loses some momentum because you can see final momentum is different, right? So it loses some momentum. So where is the momentum going? The momentum, it has been transferred. Momentum is transferred to what? To the plate or to the earth. So momentum is conserved and some of it has been transferred to the plate or to the earth. Because the earth's size is very huge, so the movement is not significant. It is negligible. Okay. You can take this down. Okay, guys, we are going to have a 3-minute break. And we will come back at 8:08. Right? Okay. Okay, so we could look at another example. Why? Okay, number one. Now, the ball 2 kg hit the wall and rebound. The speed u and v is given in a graph. This is the graph. Okay, how do you read the graph? You see, initially it started at plus 15, right? So meaning that it is moving to the right initially. So meaning that to the right will be plus sign. Any motion to the right is plus, to the left is minus. And the u is 15 ms minus 1. And then you see this line, like very steep line, goes to the negative. What happened here? Between here and here, it is the impact. Okay, it is the impact. So the impact happened at milliseconds, okay, very short period of time. So you can see that the velocity slowly decreases. If we take slow motion, then the velocity hits and then it deforms, slowly decreases, hit zero, and then move in opposite direction. So before moving in the opposite direction, it has to stop first. That is the turning point. The turning point happened at when the green line crosses the x-axis at this point here. That is the 0 point, right? So that is, it is at rest momentarily. And then it reverses direction and leaving the wall with a velocity of 10 meters per second. Okay, so the graph looks like this. And you need to calculate the change in the momentum, right? Same the way we do it, change in momentum, mv minus u. Okay, 2, so v is negative 10 minus 15. That's okay, negative 50 Newton second. Okay, calculate the impulse. The impulse is the same as change in momentum. So I equals to change in momentum, same as negative 50 Newton second. C, calculate the force acting on the ball. Okay, force equals to mv. Okay, that's change in momentum divided by the time. So we have negative 50 over time. Okay, we get it from the graph, 0.05 minus 0.03. So time equals to 0.02. This is the impact time. So divided by 0.02. Negative 2,500 Newton. This is the force acting on the ball. Add one more. D. Deduce quantitatively the type of collision. Okay, quantitatively meaning that you need to calculate. So half mu squared, half times 2. That's 225 joule. And kinetic energy after times 2 times 10. We don't need to worry about the sign because energy is a scalar. Okay, so you don't need to put a negative here. So square equals to 100 joule. Is it the same? Not the same. So there's kinetic energy loss. Kinetic energy is not conserved, so this is inelastic. You can just see from the speed. Coming is 15, leaving is 10. So speed has reduced, mass is the same, 2 kg, 2 kg. So kinetic energy is reduced. So this is inelastic collision. If elastic collision, then the graph, how does it look? For elastic collision, meaning that it travels at 15 meters per second, after bounce, also 15, right? Then your graph will look like symmetry, okay, up, down. So this one is plus 15. This one will extend to plus 15 as well. Minus 15. Then like this. This would be a elastic collision graph. Okay, take this down. Take a screenshot and then I go to the next one. Okay, now try this. Everybody, okay, you do this and then let me know your answer in the chat. This one you need to find the, you need to use density, yes. Okay, density equation you need. Because you see, F, you want to find the impulsive force, mv minus mu, right, over T. But the mass is not given. You don't know the mass of the water, and the water flows continuously. Okay, so you don't know what is the mass. So what you can do is you take the mass of water coming out per second. What is the mass of water hitting the wall per second? And what is the volume of water hitting the wall per second? The answer for this is 50 Newton. We'll discuss in a minute. Anyone got the answer? Okay, water issues horizontally from a hose of cross-sectional area 5 cm squared at a speed of 10 meters per second. The water hits a vertical wall without rebounding, meaning that when it hits, it stopped there. Okay, now find the magnitude of the force acting on the wall. So that's the impulsive force. Given the density is 1000. Okay, now because the water flows continuously, so we cannot find the mass of the water. The velocity we already know, right? The v is 0 and the u is 10 meters per second. And also we don't have the time. What is the impact time? Okay, we can use the speed. Now, you know that the water is flowing at a speed of 10 meters per second, correct? If we take the opening of the hose, we start we calculate, we take a stopwatch. When the water reaches the opening, before they come out, I press the stopwatch. I calculate 1 second, just 1 second, and then I stop the stopwatch. I observe how many water come out. Okay, how much water is coming out. So let's say it's coming out here. This is the volume of water. Let's call it V. In 1 second, right? What is the length of this column? You already know, because the speed is given. The speed of the water is 10 meters per second, meaning that every second they move 10 meters. Okay, so in 1 second, what would be the length here? This would be 10 meters. Okay, so using that, this is 10 meters, the length 10 meters. This is, we are restricting the time. We are restricting the time as 1 second. Okay, now then you can calculate how much volume is coming out. How much volume is coming out? So we call it the volume flow rate. Volume flow rate, meaning that volume per second, volume of water coming out per second. Okay, so to calculate that, you need the area. You have already got the area, 5 cm square. Okay, and you times into, this is like a cylinder, right? So 5 cm square times the length, 10 meters. Okay, so we do V over T, that's the volume flow rate. V over T equals to 5 times 10 minus 4. This one we change it to meter square. And then times into 10 meter. So we have 5 times 10 minus 3 meter cube. This is the volume flow rate, meaning that this amount of water is flowing out every second. Every 1 second, this amount is flowing out. Then, using this volume flow rate, I can calculate the mass flow rate. Mass flow rate is just like the volume flow rate. It is how much mass is flowing out per second. So it's like m divided by t. Okay, we know that mass is equals to density times volume. If this volume is per second, then this mass is also per second. The density doesn't change. Okay, per second, then this is per second. So 1000 times into 5 times 10 minus 3. What do you get? 5 kg. This is the mass flowing out per second, or the mass flow rate. Every second, 5 kg of water is hitting the wall. The next second, another 5 kg. The next second, another 5 kg. So what is the impulsive force? Using the formula F mv minus mu, we factorize out the m. So we have v minus u over t. That is equals to m over t v minus u. What is this? This is mass per second. That is the mass flow rate. So 5 into 0 minus 10. Answer, negative 50. And because it is the force on the wall, so F is 50 Newton. Okay, so this is an example on water jet, the water jet problem. All right, okay, I'm going to send you momentum exercises. The past years. Any question you have on all the homeworks, WhatsApp me. If I can answer, I will answer. If I cannot answer, then I will answer in class. So it's like every time I give the exercise, if you have questions, you text me, and then the next class I will spend like half an hour in front to talk about all the questions that you have. Okay, you can start now. You can start doing the exercises. Okay, class. We'll dismiss the class. You can log out, and I will see you next week. Okay, yeah, you can log out. Bye.
Tengah,
Alright.
tengah.